Welcome back, everyone. So today we'll learn how to represent a probabilistic model with a Bayesian net, also called BaseNet. We'll then see how a BaseNet can capture independence relationships between random variables. We'll then use the BaseNet as the basis of our probabilistic inference. We saw that a probabilistic model is defined by a joint distribution over a set of random variables. When we use the full joint distribution table to represent our probabilistic model, we run into two problems. Unless we have only a few variables, the joint distribution table is way too big to represent explicitly. It's also very hard to learn or estimate probabilities empirically when we have more than a few variables at a time. So in this lecture, we are going to introduce Bayes nets as a way to describe complex joint distributions compactly using simple local conditional distributions. The Bayes nets are also called graphical models. The idea is that we describe how each random variable interacts locally with a small subset of the random variables involved in our model. These local interactions chain together to allow us to compute the global indirect interactions. Let's take a look at a couple of examples to get an intuitive understanding of Bayes nets. Here's a Bayes net that represents a car insurance domain. It's used by insurance companies to estimate medical costs, liability costs, and property costs for each driver. There are 27 random variables involved here. Some of these variables are known, like the age of the driver, the mileage of the car, and some are not directly known. For example, the car value is not directly known, but it can be estimated based on the mileage of the car and the vehicle year. These variables all have some effect, direct or indirect, on one or more of these costs. So instead of representing this model with a joint distribution table with 27 variables, the Bayes net represents local interactions between the random variables. For instance, the driver's age affects the driving skills. So there is an arrow from the age node to the driving skill node. The mileage on the car affects the car value. So there's an arrow from the mileage node to the car value node, and so on. And here's another Bayes net used for troubleshooting a car. Suppose my car won't start. There are several reasons that may be causing this, directly or indirectly. The battery may be dead. The car may be out of gas, out of oil. The starter may be broken. There are variables that I can observe, and these are the green nodes here. And there are some things that I cannot directly observe, but they still may have an effect. These are represented here by the blue nodes. So I may know the battery's age. I can see if the oil light is on. I may not be able to tell that the alternator is broken, but that may be why the battery is not charging, and that may be why my car won't start. So instead of using a joint distribution table involving all these 14 random variables, we use the Bayes net and specify the local interactions only. So here, only variables that are connected by arrows interact directly. So a Bayes net includes nodes. Nodes represent random variables. These variables may be observed or unobserved. When the variables are observed, we can assign a value to them. When they're not observed, we cannot assign a value. We have to rely on a probability distribution. So here we have one random variable, weather. We represent it with a node. A Bayes net also includes arcs. The arcs represent interaction between the random variables. These interactions are similar to CSP constraints. So an arc indicates direct influence between two variables. We'll see later that arcs also encode conditional independence between variables. So for the random variables cavity, toothache, and catch, this is how we would draw our Bayes net. Cavity has a direct influence on toothache, and cavity has a direct influence on catch. So for now, we'll imagine that the arrows mean direct causation. We'll see later that this does not have to be strictly true. Let's build another Bayes net. So here we have n independent coin flips. Each coin flip is represented by a random variable, xi. So each random variable is represented by a node in our Bayes net. So we draw n nodes. Now, where do we put the arcs? Well, here there is no direct influence from one coin flip to another. There is no causation. So there are no arcs in this Bayes net. This is it. This is our Bayes net. When we have no arcs, we have no interactions between variables, and we have absolute independence. And here's another more interesting example. Our random variables here are R for rain and T for traffic. So each random variable gets a node in our Bayes net. Where do we draw the arcs? So in our model here, rain causes traffic. So we draw an arc from R to T. And here's our Bayes net. And here's another example with three random variables. The random variable A represents the likelihood that Anna gets an A on her midterm. The random variable S represents the likelihood that it's a sunny day. And the random variable H represents the likelihood that Anna is happy. So we have three random variables. Each random variable gets a node. We have these nodes so far. The question now is, where do we draw the arcs? Well, the answer depends on how we choose to model Anna's happiness. What assumptions do we make there? It is fair to assume that getting an A makes Anna happy. It's also a valid assumption to say that sunshine or rain has some effect on Anna's mood. So with these assumptions, we can draw an arc between S and H and another arc between A and H. And here's the famous alarm example from our textbook. So in this example, the random variable B represents the likelihood that there's a burglary, say at my house. The random variable A represents the likelihood that the alarm goes off at my house. Now I happen to have two neighbors, Mary and John. The random variable M represents the likelihood that Mary calls me, and the random variable J represents the likelihood that John calls me. Now the assumption here is that I'm not at my house at the time. There's also another random variable, E, for earthquake. Of course, the earthquake could also trigger the alarm to go off. So how do we draw our Bayes net here? Each one of these random variables gets a node, so we have 5 nodes. But the question is, where do we draw the arcs? And we can stop and think about it for a second. Basically, the burglary has some direct effect on the alarm. The earthquake also has some direct effect on the alarm. John and Mary may choose to call me to chat, but if they hear the alarm at my house, they are more likely to call me. So the alarm has some direct effect on J and M. And here's our Bayes net. So now we're ready to formally define a Bayes net. A Bayes net includes 3 different things. It includes a set of nodes, 1 node per random variable. These nodes are connected in a directed acyclic graph. There should be no cycles in the graph. So we've already seen this graph with the nodes and the arcs between the nodes, but now we're going to add one more thing. We're going to add a conditional probability table for each node. So with each node, we're going to associate a CPT, we call it, a conditional probability table. This is a collection of distributions over node X, one for each combination of X's parents' values. So with each node, we're going to associate a conditional probability distribution that gives us the probability of X given some values of its parents. And the Bayes net is actually the topology, the graph that we have seen before, plus these local conditional probabilities. And the beautiful thing about Bayes nets is that they implicitly encode joint distributions as a product of local conditional distributions. So to see what probability a Bayes net gives to a full assignment, we simply multiply all the relevant conditionals together. So the probability of x1, x2 up to xn, the joint probability, is nothing but the product of the probabilities of xi conditioned on the parents of x. We'll see some examples next. Let's go back to our traffic and rain example. Here's our complete Bayes net. In addition to the nodes and the directed acyclic graph we have added probability tables associated with each node. Node R has no parent, so it gets a simple marginal probability table. Here P of plus R is 1/4 and P of minus R is 3/4. T has one parent R, so node T has a collection of distributions over T, one for each combination of parents' values. So here we have one parent, so we have a subtable for plus R and another subtable for minus R. So this represents P of T given plus R, and these two rows represent P of T given minus R. We'll see later that we'll merge these subtables and we'll just add a column here for the values of R. Now let's say we want to compute the joint probability of plus R and minus T. How do we do that? We were told that Bayes nets implicitly encode joint distributions as a product of local distributions. We look at the local distribution here, so we have to pick the row that matches our variables here. We have plus R and minus T, so we have P of minus T given plus R times P of plus R. We know that because we have a Bayes net here. All right, and now we just look up these values. So P of minus T given plus R is 1/4 and P of plus R is 1/4. And we can compute the joint probability from the Bayes net. We didn't have to store the joint probability in the Bayes net. We just stored the local probabilities, and we are still able to compute the joint probability. Let's go back to our alarm network example. So here we have 5 nodes. Each node is going to have a probability table associated with it. So B has no parent. It's a simple marginal probability. P of plus B is 0.001. P of minus B is 0.999. E has no parent either, so we also have a marginal probability for E. Now let's look at node J. Node J has one parent. So for node J, we're going to store the conditional probabilities of J given A, given all possible combination of the values of the parent. Since we have one parent here, we have two possible combinations, plus A and minus A. By the way, all these variables here are binary. Their domain is true and false. We write that as plus and minus. All right. So for J, we store the conditional probability table, the CPT, corresponding to probability of J given A. So probability of plus J given plus A is 0.9. Probability of minus J given plus A is 0.1. So this is one subtable given a value of plus A of the parent. And here's the other subtable. We just merged the two subtables. Note that these don't add up to 1. Each subtable will add up to 1. So probability of plus J given minus A is 0.05 and probability of minus J given minus A is 0.95. And we do the same for M. M also has a single parent, A. So we have two subtables for P of M given plus A and minus A. So these are not joint probabilities, these are conditional probabilities. And finally, for A, things are a bit more complicated because A has two parents. So for A, we have to have a subtable for all possible combination of the values of the parents. So here's the subtable corresponding to plus B plus E. There are two rows here. We can have plus A and minus A. Or we could have plus B and minus E, and we have this subtable. Note that these values add up to 1. We have a subtable corresponding to minus B plus E, and finally a subtable corresponding to minus B minus E. So we merge all these subtables into one conditional probability table. So what this number means, this is not the joint probability of plus A plus E and plus B. This is the probability of plus A given plus B and plus E. So let's assume now that we need to compute P of plus B minus E plus A minus J plus M. This is a joint probability that there was a burglary, no earthquake, the alarm went off, John did not call, but Mary called. What is this probability here? Well, we're going to be able to compute it from the BaseNet, from the probabilities listed here in these tables. So the joint probability is the product of the local probabilities. So we have plus B here. B has no parent, so we take the marginal probability of plus B. We have minus E here. E has no parent, so we take the marginal probability of minus E. We have plus A here. A has B and E as parent, so we take the conditional probability of plus A conditioned on the parents, and the parent values here are given here by plus B and minus E. So we look up this conditional probability in the table here. It's 0.94. And then for minus J, we take the local probability of minus J given the parent plus A, that's 0.1. And we do the same for plus M. It's probability of plus M given plus A. So we read all these probabilities from the tables, we plug them in, and we find our joint probability. So we said that the BaseNet allows us to store joint distributions compactly. How big of a saving are we talking about? Let's take the simplest case where all the random variables are Boolean. If we have n random variables, the joint distribution table for these n variables has 2 to the power n rows in it. Now let's build a BaseNet with these n variables. We'll assume that each node has up to k parents. The size of the probability table associated with each node is big O of 2 to the power k plus 1. Since we have n nodes, the size of all the probability tables stored with the BaseNet is big O of n times 2 to the power k plus 1. So if we compare 2 to the n and n times 2 to the power k plus 1, we see that for larger n, we get huge space savings with the BaseNet. It's also easier to come up with the conditional probabilities as opposed to the joint probabilities when a large number of variables is involved.